Okay, hi, welcome everybody to this tutorial down the rabbit hole, a 101 on reproducible workflows with Python. Surely you're asking who this person is, and I'm Tania. I'm the same Tania that submitted the tutorial, just with a different name. And I work as a research software engineer at the University of Leeds. I know a lot of people haven't heard about what a research software engineer is, so basically what I do is I work with a lot of researchers and research institutes to develop better software and better code to make more open, more reproducible, and more robust research. There is my GitHub and my Twitter tag if you want to follow on. Most of my tweets are about reproducibility, sustainability, and a lot of cat gifs. So I imagine that most of you are interested in having a reproducible approach to whatever you do with Python, either data analysis or computational research or whatever you name it. So what we're going to do today, is learn a bit more about reproducibility, why it is important, and what are the different levels of reproducibility that you can aim for. Also, we're going to use a reproducibility first approach to set up a new project. A lot of the people complain, or a lot of the researchers I work with usually complain, saying that having a reproducible workflow or having open source in the research takes too much effort or too much time. It does take a lot of time if you plan to do it after you have done all of your analysis. So the earlier you start with a reproducibility approach, the faster and the easier you'll find it, because you will have strong bases. So that's ideally what we want to build today. Also, set up and use version control to track our changes, because that is very, very important. Also, we're going to discuss a bit data management and discuss a bit about metadata. Set a reproducible analysis workflow, and this means to have it as automated as possible so that you don't have to click here, drag there, remove and rename things. So the less our workflow relies on the user, the more reproducible and robust it's going to be. Also learn more about testing, especially when you're doing research or data analysis. Tests tend to be neglected, and they shouldn't. So we're also going to consider where we have to put our tests, the different tests that we can add, and how to do it. Also, we're going to follow with project's provenance. Has any of you heard about provenance at all? Raise your hand. A few hands, that's more than what I was expecting. So we're going to discuss what is provenance and why you want to keep a track of it. Also how to run our automated tests, because you can run your tests on your computer, and that's great. That tells you that what you're developing on your laptop or on your desktop works there. But what if your colleagues or your collaborators or the world want to use your workflows? You want to make sure that that works in any computer or in any operative system. And also we're going to learn how to share your analysis with the world and how to be credited for it. There is something that I always say, and people find it very cheesy, but you have to treat all your digital assets with love and respect, and that includes your data and your code. Yeah, I'm very cheesy, and you're going to see that on my slides. Also, no questions about my accent. No questions, please. I have a Etherpad there, and I'm very happy to see that people are jumping in. For those that don't have access to the Etherpad, please use this link. It is case sensitive. So it is good.gl/A6 capital T E W8. You've heard a bit about me now. So on the Etherpad, I added a small icebreaker just to know what kind of people are here. I want to imagine that some of you do data science or research or things of the sort. But I also see that people are saying that they could eat chips and salsa. Hey, I like that. Tacos. Who's the other tacos? Where are my tacos fellow? Yes. Egg in a hole. That's an interesting. Pizza. Grandma's ravioli. Yes. And, I see a lot of people that this is their first PyCon. This is my first PyCon as well. But I do a lot of teaching and a lot of public speaking. My work involves a lot of teaching. Okay, so let's get started with the core of this tutorial. So, introduction to reproducibility. And I just want to call this everything you wanted to know, but you were too afraid to ask. Every time I think about reproducibility, I just can't stop but thinking about Pasteur, because this individual was very meticulous when conducting his experiments. He was very good at documenting it, and usually would tell their peers about the advantages of doing it, and he was laughed at. Why not? So, thankfully, he didn't care about it, and everything he did was very well documented. It's thanks to that documentation that we now have things like antibiotics. Beers. You can drink beers without dying. And that is all thanks to his reproducibility and meticulous documentation. After a few years, then their peers started realizing that they could follow along, along his notes and reproduce and verify that what he was saying was actually true. And that is actually what we want to do. We want to make sure that all of our code, all of our analysis, all of our research has that seal of proof, saying this is real, this has been verified, and you can trust me. And I'm sure lots of you will have read on the internet, seen things on Twitter, seen things on Facebook claiming that there is a reproducibility crisis. But I'd rather say that this is a reproducibility chronic problem. Because, as I said, incentivizing reproducible research has not been a primary focus of research, but we can now change it. I'm just going to go over a couple of examples of what can happen when things are not reproducible. Has anyone read about this at all? No? Okay, so this is study by Reinhardt and Rogoff basically set the basis for all of the austerity measures that were taken in Europe and the US a bit, mainly in the UK. So all of our austerity measures were based on something or a study that researchers did on Excel. It turned out that a few years later, or a few months later, a PhD student was given his very first task. And that was to reproduce the results that led to this austerity measures. It turned out that, in Excel, you're doing some formulas or some computations. You have to drag that with that little cross, you have to drag it to the very end to get all your formula applied to all your data points. It turned out that a couple thousands of points were missed out. Yay. Great, yeah. So we missed a couple of thousands of rows, and you can say, well, how much can that change? Well, it probably wouldn't have much of an impact if it were just for personal consumption. But then when countries adopt those results to dictate how they're going to spend their budget and assign budget to different things, it does put the things into perspective. This is one of my all-time favorites, and not because it's a good thing. But a few years back, stem cells was the most promising area of research, because obviously that meant that you could take any cell and pretty much regenerate any of your organs and be a more healthier version of yourself. Haruko Obokata was a student of one of the pioneers in the area of stem cells, and she was a rising star. She published incredibly amazing results. Within a year or 2 years of of getting her PhD. She had her own lab, millions of dollars in grants. She had like her life laid out in front of her. A few months later, obviously because her results were so good, everybody around the world tried to reproduce those results. You had big labs of 20, 25 individuals all over the world trying to reproduce those results, and they couldn't. It didn't matter how much task force they put in, they just couldn't do it. It turned out that she got so frustrated during her research of getting null results that she started fabricating data. And she started manipulating her plots. So all of her grants, all of her results were based on fabricated research. And there was no control on whether that was real or not. And a lot of people say, well, I'm not doing computational intensive research, but you're using Excel to get your plots, or you're using Excel to get your analysis. So that is software at the end of the day. And every piece of software, that's probably my personal opinion, that you're using for your research or for your analysis has to be verified somehow. Now, on the brighter side, sorry for giving you a very sad time, Philip Stark, I don't know if any of you know him, he started this campaign calling Science is Show Me, Not Trust Me, just to tackle all of these issues of people publishing amazing results but not having any hard data or not having any hard measures to back it up. For example, following on the Reinhardt problem, relying on Excel for important calculations is like driving drunk. No matter how carefully you do it, a wreck is likely to happen. And that comes down to reproducibility. Because you depend so much on your user. You depend on your user to add the data, to scroll that, to pull that cross to get all your calculations, then click here, click there. So you can't really track exactly all the same steps that your individual or your researchers did. Another thing is the reproducibility crisis is like climate change. It is of vital importance, but there are very few people and very few groups aimed to actually convince the others that this is a big enough problem for us to take action. And here I've said so many times the word reproducibility. And I can just see some of your faces like, yeah, well, what is it? I'm glad you asked. Not. I'm going to refer to Roger Peng. And in 2011, he started defining what reproducible research in computational science is. And you can have different levels of reproducibility. At the moment, if we only publish our results, we are saying that we did something, we present our methods, and that is it. So this is the lowest level that is now the standard. It's publication only. If we share our publication plus the code, it's moving slightly towards reproducibility. If we share our publication, our code and data, it is getting more reproducible. And then if we can give all of our users or all of our readers all the tools that they are going to need to reproduce, to get to the very same results that we had, that is full replication. So this basically covers 3 levels again. Reproducible, it's, let's say, I have this data and this code, and I get these results. If I then give you the very same version of that data and that very same version of that code, and you run it and you get the same results, that study is reproducible. That is level 1. Level 2 is replicable. So I can have my code and my data and get a result. Then if you have collected your own data for the same problem, let's say that you want to verify the same hypothesis, and you have my code, and you get similar results for the same hypothesis, that is a replicable study. That is replicability. The third level is robust. I have my data, I have my code. One of my collaborators can have the same their data, and a similar version of the code. What comes a bit of more of a shock is a third collaborator can have another data, the same structural code, but they can even use different tools. So instead of using Python, they might be using R, or they might be using MATLAB. It doesn't matter. That is the thing. It doesn't really matter. As long as they get similar results again for the same research question, for the same hypothesis, that is robust. Does that make sense? Those three different levels. And I think as of today, we're barely scratching this first level. And this is what we're going to do today. Make a jump from this very basic of non-reproducible, non-replicable research to at least get to replicable research and replicable workflows. And why should I care? I imagine that you all care because you signed up to this workshop or to this tutorial, except for a few that I know they clicked on the wrong tutorial. I'm sorry. The first reason for you to care about reproducibility is convention. It is like us deciding that we're gonna drive on the left or the right side of the street. So a clue or a cue of civilization is following conventions that constrain your behavior a little in the name of public safety. In this case, when we restrict our behavior and our standards of research, then we're promoting and incentivizing better research or better analysis or better data science. From a technical scenario, for your personal intake, your objective is to have a complete chain of custody, and this is provenance. That means that you can exactly tell what version of your data and what version of your code you exactly use to get a given set of results or a given set of figures. That is provenance. So you know exactly at every point where your results come from. So let's say if you're using version control and you produce results and research that is going to give you a Nobel Prize, and you have made modifications since your nomination, you can always refer back to that version that will give you the Nobel Prize or whichever other award you're going for. From a practical scenario, imagine that you have all of your amazing data analysis, your machine learning models in your personal computer. Unlucky enough, someone will just sneak into your office at night and delete everything, like all your codes, all your results, everything is gone the next day that you go back into your office. Everything except your code and your data, because of course, after this workshop, you'll have everything in a repository, you'll have everything safeguarded. It doesn't really matter if everything gets deleted. Then the next day, you can just go and reproduce everything. You can automate everything so you can get all your results, all your tables, all your figures, instead of spending, again, 6 months, a year, even 2 months trying to get all of those results back. Wouldn't this be great? Wouldn't this save you a lot of time and stress? Yeah. Better yet, what happens if you leave the project, if you get an amazing job somewhere else, and you get your collaborator, you just leave, or you just decide that you have enough science, enough Python, enough data science in your life, and you decide to put a taco truck. Yes. It would be great if anyone could pick up your work at any point and then just get back to you where you were. That would speed up research, that would speed data science so much. Also, trust me, these will help you. Your future self will thank you so much. After a break, if you go to, I don't know, Hawaii for long holidays, or you go to Africa as an engineer without border or something, and you come back 6 months later and look at what you were doing, more than likely you're going to forget at least a third of it. So your 6 months future self will thank you now. And it doesn't have to be 6 months, I tell you. I've already mentioned this point, but again, from a sustainability point of view, this speeds scientific progress. It contributes to open source and our beloved community. And we also acquired more varied, highly valuable skills. And this is key, because these are skills that are lacking everywhere. So when you start introducing reproducible workflows, that will also give you a bit of a heads up or a bit of a margin to get better jobs. So we all want better jobs, or at least jobs that we enjoy a bit more, if you don't enjoy your current job. And my all-time favorite, increase the buzz factor. Has anyone heard about the buzz factor? Ah, yes. So I want you to think about one of the projects that you're working on at the moment. How many of the main contributors will have to be hit by this buzz before the project stops, before the project dies? Okay, have you got that number in mind? Okay, it says 1, 2, 3, 5, 10. So we all have very small buzz factors. So if we die, if we're hit by this buzz, if we are the one driving the bus, more than likely a lot of our projects will stop. So we have all of this reproducible analysis in place. Who cares about this bus? Discussion time. Yay. This is my favorite, well, some of my favorite times. And I want you to make teams of 3 or 4, just round yourselves and discuss what measures do you take to ensure your analyses are either reproducible, replicable, or robust, and whether you have encountered any barriers to reproducibility. If you have, what are these barriers? And also, just a short thing about why you are actually here. What do you want to achieve after today? Even if it's just the one thing that you say, I want to learn how to keep track of what I did, or just, I don't care about reproducibility, I just want my code to be citable, okay? And I'm just gonna give you 10 minutes to do this. Write down your results on, or your discussions on the Etherpad, and I'll just be going around. So does that sound good? Sorry? Did you publish the slides? Yes. The link is on the Etherpad. Yeah. Hello. Yes. If you want to follow along the slides, the link to the slides is here on the Etherpad. So you can click there and you're going to go to the interactive version of them. Yeah, I'll have to.
This mic's on right now just for noise.
Yeah.
I
So.
just want to fix your microphone just a little bit too.
Oh, is it? Where?
Yeah, just spin it up just a little bit.
Is it too quiet?
No, it's just if it keeps going,
Oh,
if
down.
it keeps falling down, it gets harder and harder to pick
Okay.
up.
Yes. Thank you. Okay. I know you are all enjoying very much your discussion, and it's very nice to see you all discussing all of this. Often when I have this kind of sessions, it sometimes feels like going to therapy. You know it. So yeah, sometimes it feels like going to therapy, and you realize that your problems are usually not just your problems, so you feel less lonely in this world. Excellent. So what measures do you take to ensure your analyses are reproducible? Oh, yeah, reproducible, replicable, or robust. It is okay to not have any measures, because that's what we're going to learn today. Detail logging. That's a good one. Thoughts and prayers. That was me. Back in the day, that was me. Jenkins. Bamboo or Travis, it is all continuous integration. We're going to be using Travis during this workshop. Travis, not the band. I do love the band. Save scripts or Jupyter notebooks and ensure that the inputs are properly managed. Naming is key. Static citable inputs when doing research. Database functions. Whoa. Documenting that was done and how my team can reproduce the work. Okay, there are different levels of documentations, but I do like that. Airflow. Version control, virtual environments in Git, Docker, Jupyter Hub. GitHub, test, checklist, documentation, Gitflow, Bitbucket. It seems like we're in a nice place. It's okay if we have a mixed bag of abilities and skills. Don't worry about it. We have to start somewhere. What are the barriers? Not yet, but issues with proper memory management, environments changing. It happens all the time. Again, environments, not having the data or rebuilding workflows. How do you write shared library code for enterprise? Data shift, unclear commenting and change logging. Yes. Moving to a new code repository. Risk losing history and creating a mess. There is a Twitter account for Git Horror or something. Yeah, I'm gonna look for that. Hesitancy of others. Yes. Running up projects with different requirements. Hard-coded data paths. Hard-coded data paths are the evil. Moving from old technologies to newer tech stacks. Ego. Keeping things simple for all levels. I think that is also one of the big problems. I work with a lot of researchers, and data science is no difference, really, because I work a lot with people in machine learning, too. There is this thing in academia and research and data science that you are surrounded by amazing people that are very brilliant and intelligent, and you always feel that you have to meet certain standards. So you feel that some people feel that by sharing their code or sharing their workflows, someone else is going to find a mistake, and that can't happen. That just can't happen because they can't put themselves in the spot. And this goes a bit more with culture change. I think we have to also make science and data science more human, to make it more open. But we can discuss that later. Trying to keep it simple, convincing others to buy in reproducibility. Yes, it is with. Data confidentiality. I like that one. Time constraints and priorities. And someone started doing my quick poll. Okay. So, what can we do to make our analysis more reproducible? We can share as and when possible, because sometimes we have these issues of confidential data. Well-documented codes, documentation, different levels is key. Data used to produce the results, the details of the workflows used, and information on how to cite our work. This, I'm going to put so much emphasis on this because this is key. We need to allow others to build on what we've built before and being credited for it. That is a key. But before we move on, did anyone have any troubles with the instructions I sent? Have you got the data? Have you got the scripts? Have you got everything working? Yes. If you get stuck or you have any problems, at any point, ask me. We have Dorota here, that is our amazing TA for the day. And also you have some sticky notes that she's already handed to you. So if at any point you get stuck, just place your sticky note here, and we can keep an eye on how you're doing and whether you need any help or assistance. And are you ready to get your reproducibility skills on? I love those cats. And because this is all down the rabbit hole, every adventure requires a first step. Project plan. That is always the first step. How many of you do a proper project plan or a proper data management plan before starting a new project? Yes. There are some things that we have to consider to set yourself for success. And this is what I want to do. Help you set yourself for success. Because nobody wants to do scrummy data science. Nobody wants to do scrummy research. And I want you all to succeed. So whenever you're starting a new project or building on a project, you have some questions to ask. Think about possible scenarios and what tools can help you to achieve this. So for example, what is going to be your MVP or your minimal viable product or your final product? How is this going to look like? Is this going to be your thesis? Is this going to be an article? Is this going to be an internal report? A new library or algorithm? How is it going to look? And match it with the tools that you're going to need. It is okay to sometimes not know what tool is the best one, but at least you know what you need to aim for. So it can be a LaTeX, Jupyter notebooks, scripts, containers, whatever you want. Who will use my data and code? Is it only going to be for personal consumption? Is it my colleague? Are there other groups? Is this the world? Is this going to be deployed in AWS? And what are my helpers? So we can use Git. We need to also think about an appropriate license because licenses are also very important. We need to think about the documentation, where we're going to deposit the data, where we're going to put the code. Who and how long will this be maintained for? Who is going to look after this if I leave? Do we have enough budget for it to be maintained? Is it going to be 6 months until I finish my studies? Do we want our package to be part of the open source community and have the community to contribute to it? So we have to think about that. And again, what about all my other assets? What about my data, my slides? Because if you're giving a talk, your slides are also important, your articles are, your workflows are. All of your research assets or scientific assets are important. They can be shared, they can be published, deposited in a repository. And you have things like Fixture, Zenodo, institutional databases, web pages, so many options. So these are the minimum number of questions you have to ask yourself every time you start a project. And then you can move on. Now, have you got a minute to talk about open source? One of the nicest things about Python is that it is open source. And when we make our work open source, that allows others to collaborate. It also allows us to establish long-term relationships, maintain our code for longer. And Lorena Barba thinks that open source is very tied directly with the method of science. Now, something that is very often overlooked is licensing. When you are starting code and you're starting a project that is going to involve a substantial amount of software or even a tutorial or a workshop, you have to think about license. And ideally, I would want everyone to make their code and their data open. It is not always possible, but that would be my ideal. And that means that the content can be freely used, modified, and shared. And that is basically the open definition. Now, a few things. Simply making this public, if you put your code in GitHub or in Bitbucket or GitLab, it does not make your project open source. A lot of people think, oh, well, it's in GitHub. Anyone can use it. Yes, but no. Because every piece of software has copyright and intellectual property. So without the license, people don't know whether they can use it or not. So a lot of people are just going to decide not to use it, just to not infringe this copyright. So you want people to use your project, you want people to benefit from what you're developing, add a license. Always add a license. When we talk about open licensing, we normally have two big branches of this. The first one is permissive. So basically, this gives us a lot of freedom. It is very open. So I think one of the main clauses of this is that authors need to be credited for the work. Let's say that if I use a piece of software and then I build upon that, or I have been using it for my research, I have to credit the authors, which is only fair. And this kind of licenses are MIT, BSD, and Apache. We have also the copyleft, and they're also referred to as share-alike licenses. And they restrict the use of software by requiring that any software that is derived from this original one has to be also under the original license. And the very clear example of this is the GPL license. It is still open source, but it is open source on the basis of this restriction. So when possible, I would encourage you to use the permissive licenses. MIT, BSc. If you don't know where to start, you can always visit this website that is choosealicense.com, and that gives you a very nice, friendly introduction on what are the differences between these licenses, especially on the appendix. If you go to the appendix, it has all of the free open source software licenses, and you can pretty much compare all of the items and all of the clauses and make an informed decision. Now, even though we have these open source licenses, that doesn't mean that they are all compatible. And also, compatibility is directional. So for example, if we have a BSD license, let's say that I have software that I chose a BSD, it is only compatible on the backward stream with another similar permissive license, and forward compatible with permissive, copyleft, and proprietary licenses. So anyone who derives your work from yours can choose any of these licenses. So it's always good to know this when you're developing software and when you're using software from someone else's, to know what license you can assign to your own project. Excellent. So this is the very minimum we have to think first. And this is more like the theoretical side, like think about what you want to do. And, well, I imagine that you're like, well, now I'm so ready to start with my software. I'm so ready to get my workflow. Where do I start with? Well, we're going to begin at the beginning. And my quick poll. You have probably 2 minutes, not 5. I know some people have already done this. And can you tell me which is your to-go to start a new project? which are your files, directories, data structure, or naming conventions that you always stick to? Do you always have a data directory, figures, results? 2 minutes on the Etherpad now. Excellent. I'm just going to go over some of the answers. Everything in one folder, sometimes subfolders. I use input and output so that the data directory is sorted to the top of the project. Oh, well, underscore input, underscore output. Copy a folder directory structure into all your projects, source data, derived, blah, blah, blah. I always have a utils.py and a test.py. Something underscore v1 underscore v2 underscore v2 underscore test. Conflib logs organizational approved structure so that anyone in the organization will intuitively understand it. Visual Studio Enterprise structure for data files. Oh, I like that one. Yeah. Date. Weird slug, project code, some suffix, create a new Git repo, good old-fashioned whiteboard, cookie cutter-like structure, different folders based on functionality, pre-template, common comments in one folder, models, views, controllers. I would create a Python environment, code and data, but I'm getting better ideas evolve. Data code test, results directories, blah, blah, blah. Excellent. So we have, again, a mixed bag. We're going to start creating our project structure, and this is crucial, again, for your success, because a good project layout ensures that we're going to keep integrity of our data, that our project is going to be portable, and that is going to solve all of those problems that people were mentioning before about having hard-coded paths to the library, to the raw data or to other of your packages. And it's also easier to pick the project after a break. There is no single way. I'm going to say there is no single way or a right way to do this. But again, I'm going to just make use of the power of convention. And especially like this quote that is a place for everything and everything in its place. Meaning that although my project is going to be self-contained, everything has to be an intuitive place allocated for it so that anyone can know where to look for things. And this is a proposed project structure. This is a project structure that we're going to use. So we have our root, then we have license, always license, then a README where you're going to put a bit of description of what your project is, how people can use it, how do you run your script, something. Bin, your configuration files, then a folder for your data, and at least you have to have something for your raw data, processed, that is your final plain wrangled data, interim and external, if you have data coming from other sources, for example. Docs, that is for your documentation. Notebooks, if you have Jupyter notebooks or things of the such, or Markdown. Reports, if you're going to write internal reports or an article for Nature or Science or whatever you're doing. Figures, output, another for your source code, and inside your source code, again, you need to separate it. Knowing which source code is being used for your data, for your models, for your tools, or visualization. Not all of the projects are going to have, for example, a config, or, and I'm open to discussion this, or a bin. We probably won't have always compile codes or binaries, but it's good to know. And for this, you can do this manually, you can use a shell, you can do it as you want, but in this case, we're gonna use an opinionated approach for this. And I'm following an opinionated approach for this to have a convention. Because, as I said before, it is okay to have, it's good to have a convention so that everybody knows where to look for things. And we're gonna use Cookie Cutter to create our base file system and our supports documents. So you should all now have your code environment. So we're gonna start by activating our environment. Hope you can see here. So we started with source, activate repro-python. And for those that have never used code environments before, that ensures that we all are using the same libraries, that we're using the same packages. And once you activate it, your shell, they're interchangeable terms, shell, terminal, command line, should tell you that now your environment is active. So you should have a legend saying repro-python now somewhere. My terminal might look a bit different to yours. It is okay, especially for those that are in Windows using git bash. If you're using git bash, it changed a bit. I just made it so you can see better. And then the next step would be to create our project structure. So wherever you want to create this in your computer, for example, I'm going to create this in documents, then Git, you can start typing and then use tab for auto completion. And that is where I'm going to create a folder, because I know that I normally put everything that goes into Git or GitHub into that folder. So once we create Cookie Cutter, GH, we grab Cookie Cutter, reproducible science. I think that is it. We're going to be using the science cookie cutter. There is another one for data science. The project structure, the layout that you have, that you get are very similar, almost interchangeable. It just changes a little bit. So is everyone here? No? Yes? If you're not here, put your stickies on so I can see. And then once you click and you enter that command and click enter, it is going to ask you for, oh, of course, I made a typo. So once you add this, it's going to ask you, it's going to prompt you for some details. So first of all, it's going to ask you for your name. So for example, for me, it's Tania Allard. And my email, then my GitHub username, it's that. And project name, you can call your project anything. So I'm just going to call it reproducible Python. Now, it gives you the option to choose a project slug, and that is how the directory or your folder is going to be called. If you leave it as it is, it's just going to create a directory called reproducible Python. I tend to just leave it like that because I like the slug convention. So I just leave it like that. Then you can give a project short description. And this is, for example, my reproducible workflow. Or you can say my super awesome data science project, or reinforcement learning, or anything. Release date. It is by default going to assign today's date. You can assign a different date, but I'm just going to leave it as it is. Version, it starts normally with 0.1, 0.0. Again, if you want to assign a different version, you can assign a different version. Or if you follow a different convention, for example, like V1 something, you can use it. I'm just going to accept the default. Okay. So I'm just going to... Oh, sorry. So if you go, you should now see this directory or this folder. And it's going to create all of this folder structures that I told you before. So you're going to have a bin, a config, data, docs, src. It also includes an authors MD file. So So if I look at inside that folder, it's going to only add myself, using those details that I gave from the command line. And it also gives you a license. By default, it's going to give you a BSD license. If you want to change it for MIT or Apache or anything that you want to change it for, do it before you commit it to GitHub. You commit it to Git and push it to GitHub. It assigns again your name from the name that you gave on the CLI client or the command line client, and it's pretty standard. And it also gives you a README. And what you're going to see in the README is the title of your project, followed by whichever description you gave, and it lays out the project organization. So you can see what are the default directories that you have in there. And that already gives you a very good basis to start working with and start putting your files inside. And you don't have to do anything. Also, by default, Git, who's familiar with Git, with version control? Oh, good. So you will know that by default, when you create empty directories, you can't commit that to Git because it just doesn't track directories, but it tracks files. It adds by default a .gitkeep file. It's empty. It is just named file, and that will pretty much force Git to keep track of those folders. So I've said already version control. So a version control system, it can be Mercurial, it can be Git, anything. It helps you to keep track of every modification that you're doing. So if you delete a file, it'll track it. If you add a file, if you modify a couple of lines, it keeps track of it. And some of the advantages are that they enable collaboration without stepping on each other's toes. So you can work on your local computer, your collaborator can also do it, and without you deleting what the other person is doing. It not only keeps tracks of the changes that you're making, but it also gives appropriate timestamps. So you can tell exactly when that modification was done. It gives you a unique alphanumeric identifier, so you know what version of the code it is. And you can access your work everywhere. And it's pretty much like having something like this. So let's say this is our first version. You create your new file. Then if you make some modifications, you can then track if you created a new file or if you modified a certain file, and so on and so on. So you have all of this snapshot. So think of we call this a git commit, and it's like a specific snapshot of your project at that given time. Again, these are all of the advantages. And basically, it also serves as your time machine. If you make a mistake at any point and you need to roll back to a previous version, you can always do that. And yeah, that allows you to never lose your project. And we've all been there. We also have these weird versions or very weird naming conventions, and we don't know what we're looking at, and that will prevent us from sending Excel files, Python scripts through email and having lots of different versions. So the first thing we want to make sure is that we have Git properly configured in our computer. If you don't know if you have done this before, you can just type git config -- list, and it's going to show the different configurations. So in my case, I have my user email and my username. I have lots of things. Ignore all of my things. But as a very basic starting point, make sure to add git config -- global user.name, add your name, git config -- global user.email from your command line. Are we everybody on the same page? Have we got our Git configured? Do you want 2 or 3 minutes to get this on? Okay, put your stickies on and I'll just be going around. For those that have configured this, you can start by committing this to Git for those Git ninjas that we have around. Okay. So it seems like everybody's got Git configured now. And what we're going to do, we're going to make sure that we are in our directory. For example, I called it reproducible Python. You could have called it repro project or wherever you want. And we're going to do a Git init. We make sure that this way we're telling Git, we're going to create a repository here, so I want you to keep track of the things that are changing. And if we type in git status, it's going to identify all of these files. So it tells you have this on track files. This is something new. You added this. And we're going to do git add dot, and that is going to add all of that. So if we do, again, git status, now Git knows what is happening. So it goes from, you have all of this, but I don't know what you did with this, to this is a new file, this is a new file. And we're going to do a git commit -m. This git commit is taking those snapshots that I told you before. Every time I do a git commit, I'm taking a snapshot of my project at that very specific time. So the git commit, and for example, create initial project structure. So if I do git status again, it says that there is nothing to commit. Everything has been snapshotted at the time. We don't have to worry about it. And that already gives you version control, so you know what, from the very beginning what is going to be changing, and you have your directory. I think we have a break, and I'd rather take the break now before going on to data management and adding the data into scripts. So shall we say come back here in 15 minutes, so you can use restrooms, I was going to say, the restrooms, or get a coffee or whatever you want. If you're having any problems, you can just always come and ask me.
I have two people, like the guy is having problem with cookie cutter, so maybe
Great. So now we are ready to start talking about data. And we're going to start with data. Raw data are sacrosanct. So never, never, ever touch your raw data. Not even with a stick. Not at all. Okay? So our raw data is where we get our data from, or data, as some people call it. And I always get this question when I start telling people to version control their data, to version control the code. Like, so should I version control my raw data? Like, no, because that should never change. All of your processing, all of your data wrangling needs to be done on copies of that data or subsets of the data. So theoretically, there is no need to version control your data. You can put it in a safe place. You can put it in a repository, in a database, somewhere where you know that it is going to be there all the time.
That's right. Just that one twist that all the projects I work on are while they're running, in a sense, for say surveys running. So we actually do some version controlling of our data in the sense that this is what we had as of Monday, Tuesday, Wednesday.
Yeah.
Because the project's ongoing, and then that lets us catch, respondents updating
Yeah.
data, partway through because they participate in research.
Yeah. 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 You can do that. But yeah, some simple thing. If you have collected all your data, if you have all your massive subset, your massive data set, that is your raw data, and you're not planning on collecting more data on a regular basis, then that is frozen. That doesn't need changing. If you have a much more dynamic database, that sounds like your case, where you keep getting more data points added, then you do need to version control it, more than likely. Normally GitHub is not a good place for you to have your data, because I think you can only have up to 5 gigabytes of data. So if you have anything bigger, that can be, for example, bioinformatics or genomics data, or from social networks, or corpora for those that are working in NLP or linguistics, that is never going to be enough for your data. Your data should ideally not go on GitHub. But you have things like GitAnnex or DataLad, and that will allow you to version control your data. It will handle the vast amount of data that you're going to work with. Or you can also have your data on Fixture and create a DOI so people can cite it.
So the data, raw data is that big data set?
Yeah.
It shouldn't be safely with raw directly, raw data directly.
It should be in data. So
I think this directly will be sent to GitHub.
no, no. I'm gonna check your gitignore in a second when we go there. Yeah. But by default, also cookie cutter, what does is, by default in your gitignore, all your data files, directories, so data, external data, interim data, process data, raw, they're all ignored by Git by default. So when you push to Git, those are not gonna get pushed or tracked. So that is advantage of cookie cutter, so that by accident you're not gonna be pushing your data. If you do need to force push it, is it gonna be the case for our analysis? You can do it. You just modify your gitignore. So for this second part of the workshop, we're going to be using a dataset from Kaggle. We're going to use a wine review dataset because I like wine. Who doesn't like wine? I know some people don't like wine and they don't drink, but I do like wine. So you should now all have the data. Make sure to get your data, I think I said that word too much, into your data/raw directory. And now that we're talking about it, does everybody who got their data in the data/raw directory? Yes? No? Now that we're talking about data, having data and having raw data and versioning control it is not enough. We also now have to document our data, because as important as our code, documentation is key. And data without documentation has no value. And in this case, we're talking about metadata, that is data about data. And basically, it is information that describes, explains, locates, and makes it easier for others to find, access, and use your resource. In this case, our resource is data. So it should answer all of this. For this workshop, because we're going to be using it as personal consumption, the bare minimum for your version consumption is to create a README file inside my data directory that has at least these things. So at least the title of the project or the data set, what are some of our keywords. For example, I can give keywords like wine, reviews, magazine, and Kaggle. Where I collected this data from. So I collected it from Kaggle Wine Mag Reviews. If it has an URL, or if it has a database, unique identifier, you add it there. And when it was collected. Because this is going to be our raw data that is going to not change throughout the process, we can say when it was collected and who collected it. So please guys, please folks, make sure to create now. You have 5 minutes to create a README where you have this kind of information. Once you have done it inside your data /raw, committed to GitHub, to Git, again. So you do your git add, git commit, and then add metadata to your data. Okay, gonna give you 5 minutes, and while I sort other issues that someone was having. Yes.
Commit the data itself.
It's not gonna commit because we have a git ignore. Yeah. At the moment, it's not gonna be committed. So the only thing that your git is gonna find is your new metadata.
Thank you.
Did it work? That is a nice way to do it. Yeah, we're gonna get to those naming conventions soon. Don't, no, don't. Problems? A space. No, space between add and dot. So that it's gonna track all of your changes, and then get commit. Space minus M, and then you need to add a message, and then add whatever, and then close the quotations. Now, while we are doing this, committing the README and committing everything, also remember that every time that you are committing you're taking a snapshot, and not only you want to see all those versions, but you want to understand what you did during those different versions. So if you write meaningful messages, that will help you. Instead of just writing, ga, or I hate you, Jupiter. So also make sure that you do that. So we all have data and metadata now. Cool. Oh. Doesn't like it. So we have cursor and cursor. And now we're getting to the bulk of it. We're gonna add the code that performs analysis. We have now our structure, we have now our data. And these are the different steps that we're gonna create. First, we have a Jupyter notebook for exploratory analysis. Jupyter notebooks are excellent when you want to do rapid prototyping, when you want to do exploratory analysis, and when you want to disseminate your results. So we're going to use a Jupyter Notebook now. We have intermediate scripts that are going to generate my analysis outputs. We have a workflow. We have our raw data, and we're only interested in generating a subset of the country, designation, points, and we're going to create a special column that will give me the price in British pounds. And we're going to save all of that in a CSV. We're also probably only interested in analyzing the wines that come from Chile. So we're going to create a subset for only the wines that come in Chile, that were produced in Chile, sorry. And what would be of my analysis without plots? So we're going to create a scatter plot of the wines versus price and a distribution of plots versus wine scores. Don't worry, you don't have to write everything. I've given you this. We're just going to make sure that everything is inside the right directories. And this is for you to start getting used to place everything where it belongs. Put everything in its place. So when you downloaded the dataset for the Kaggle wine reviews, you also downloaded a directory called support scripts. It contains a Jupyter Notebook and 3 other scripts, I think. So just make sure to put them in whichever directory they belong to. So the 00 exploratory analysis will go in notebooks. The subset country will go in data. The subset data will go in data. And the visualize will go in visualization. Once you've done this, do a git add and git commit. And for example, a meaningful message for this is going to be processing scripts. Okay? 5 minutes for this. Yeah. Really? Could you download it? Everybody could download it.
Yeah.
That is so weird. I'm just gonna double check the sharing permissions, but everybody downloaded it. Oh, are you trying to? Sorry. Did anyone else have problems downloading the scripts or the data? Can everyone access the Google Drive? Nice. And also, one thing that we have to understand, when we do data-intensive anything, there are going to be lots of files. So probably you'll end up in files hell like this. I hope not. So we have to also get into the art of naming. There are three core principles for files or scripts or anything names. First of all, it has to be machine readable. That means that it is friendly with globbing and regex. So all of the use of delimiters, either dots or commas or spaces or underscores, well, not space, underscores, hyphens, everything has to be deliberate. So that will help us to find whichever file we want to find. It also has to be human readable. The best names are those that you can just straight look at the file structure or the file directory in your Finder or your File Explorer and understand what those files do. Also, embrace this log. Use semantic URLs as log. It will help a lot with understanding the names, and we're going to go into that. And also, good files names play well with default ordering. So whenever possible, put something numerics first. If you're using the date of your analysis or a date for your report, use ISO conventions. They're there for something. And this means year, month, day. I know people in the States use a whole different thing. Try not to do it. So this is a public service announcement. The correct and human understandable way to share dates is that anything else, please don't. Just don't. Okay? Again, what works and what doesn't. Report. Yeah. Have no idea what report. If you add instead a date report for SLA, you know what it is. You don't have to actually open it. My husband hates me for this, but Joey's file name has spaces and punctuation. You could do better, so you can have Joey's file names are getting better, and that is regex friendly. Figure space 1. Yeah, I'm gonna have 500 figures 1. Figure 01 scatter plot tog length versus interest .png. And this is a very good attempt, but whenever you are using numbering, try to left pad it. That way, everything is going to show in a certain order in your Finder. So start with 01, 02, 0, blah, 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 blah. up to 5,000 or how many scripts you're going to have. We're going to be using Jupyter Lab, and Jupyter Lab provides you a graphical user interface, and it plays nice with Jupyter notebooks, with scripts, and you have pretty much everything self-contained. Sorry. So from your directory, root, make sure that you're there so you can see all of your files. I'm gonna just run Jupyter space lab and click enter. And that's gonna spin out an instance of your Jupyter Lab on your web browser. It doesn't need internet access, but you can see that you have all of your files structured there already. You can spin out notebooks. You can navigate your directories. Has anyone used Jupyter Lab before? Jupyter notebooks? The good old command line only and Python scripts. That's fair. Yeah. Okay. So you'll be presented with a launcher, depending on how many. In this case, we only have our content environment active. So you'll probably only have Python. I have 2 other things. I have Julian R. But you can also get an IPython console that is interactive Python. You can spin out terminal, and you can spin out text editor, so you can do pretty much everything from there. You can do pretty much everything from Jupyter Lab. Sorry, see your file system or your file structure, and you have everything self-contained. So that's why we're going to be using it. Now the scripts, and this ties us nicely with the naming convention. All of the names, all of the scripts are named following this log convention that I mentioned before. So you have 00 explore data, exploratory analysis, 01 subset data, grade breaching pounds, and 02 visualize ones, 03 country subset. So the best names are self-explanatory. You don't really have to guess much what is inside. I'm going to give you 5 minutes to discuss in, again, your original teams. Go on to have a look into the scripts. So if you click there, you can see the scripts. Look at all of the scripts that you have. You can have, the notebooks. Oh, I don't have it in the notebook yet. Have a look at the notebook, execute the notebook, look at the scripts, and find out which are well documented, how well documented they are, and which kind of documentation you would prefer at 3 o'clock in the morning when you have a 5 o'clock in the morning deadline. And again, feel free to add anything to the Etherpad. If you want to have a go at running the scripts that you have, you can just run them like so from the root directory in your shell or your terminal, and then Python, it should just work as it is, Python, SCR, and then the path to the script, but you have to provide also the path of the data. Have a look first at the scripts, discuss it with your teammates or your partners, and write what problems you found there, and what disadvantages you see of having an analysis like this or a workflow like this. user. You should have support scripts. Oh,
So
somebody must have deleted it.
he only also shows the guy. Does
Oh,
anyone
because
has edit?
I think they had edit access.
So
I'm just gonna make sure that everything is in there. That's all right. I can see everything. Is it different? Why? Why? I can read them if you want. But okay, can you see it now? Okay, so okay, so try. I added another link, and that should take you only to the. Oh, why does it say? Mm-hmm.
So for the
01 should go here.
different data we have,
Yeah.
Yeah, and you also
should
should
I
have
run it
03.
in the notebook to be able to
Yeah, you can.
visualize the plots?
Yeah.
Okay. Should I make
So
a
this
new
is a notebook. No, just run. like this. Okay. So, okay. So, were you able to run the notebook? Yes or no? What is a good thing about having the notebook straight away and having the structure? You can run it. You can run it because we are all following the same conventions. So we're trying to find our data relative to the directory of our analysis. In this case, you all have the data where it has to be, and you can run the notebook. So you can straight away see that you don't have to fiddle with paths. And everything just works for most of it. We also are running everything inside the same code environment, so we have the packages that we need to run everything. So we don't have to fiddle and install and uninstall and update packages for most of it. Now let's see the subset data. What do you think about this documentation? Good, bad, could be improved? Meh. Okay. As basics, at least all of your functions should have a very basic documentation of what are the arguments that it gets, what it returns, and what it does. The why it does it. The how it does it should be pretty self-explanatory from the code. In this case, we have these lines of code, so we can pass the path to our data as a parameter, and run that as a standalone script. And pretty much all of the files that we have, all of the scripts follow the same rationale. And something that it has in particular is that all of the interim data, all of the data that is going to be generated as part of our processing or pre-processing will be date labeled. So if we run this analysis today, this data is going to be 2018, 5/9. So it's the 9th of May 2018, and you know when you generated that data. It has some advantages and some disadvantages, of course. But as this script stands, you have to run everything. Did you try and run the scripts? What problems did you encounter? Missing paths. Yeah, so which is a script that has a missing path? 2. Good. What about number 1? Did it work? And do you have your interim data created? So it is already there. Did the 3rd script work? How confident are we about the results? Did you look at the data? Did you have a nosy at the data? What are we getting? No? Nothing? We didn't care much? You should care. So I'm just going to run this. What is my data? Okay, so that should work straight away. And it's going to tell us, it returns as it is, the path where my raw data is being saved. It doesn't like it. Oh, there you go. So as it stands, the thing that it returns is the data that the path to the interim data that is being generated. The second one didn't work, and the third one should generate a similar subset of data. So at least we know what we're getting. We are getting a bit of a feedback, and that is always good. You can, for small scripts, you can always print things through your command line to have an indication of what is being generated. You can use more intensive logging, if you're going to have a lot of outputs, you can use log in Python, and that gives you more robust support. It works. These scripts do what they're meant to do, except for two. But it gets pretty boring because you have to run everything manually. So you have to tell Python, run this script with this data. Now Python, run this other script with this other data. So you have to keep on top of it. Our ideal is to eliminate all of that. So we discuss the documentation. And automate all the things. Because wouldn't it be nice to just have a comment to go from my shell, and then I can go prepare a cup of coffee or a cup of tea, come back and have all of my results and all my article and everything ready to be packaged and shipped. And to do so, we're going to first make sure that everything is a package, and that we're going to generate a script that will run all of the analysis, so I don't have to do these intermediate steps. But for that, we need to ensure module discoverability. As we have the scripts now, each script will generate a very specific thing. So we have the first one that will subset the data, and we get a subset. The second one will generate the figures, and you can see that they have one or two functions inside them to develop a very specific thing. And that is already giving us modularity. That also allows us to remix and reuse our code without having to duplicate code. And that is a good thing. So we need to make sure that we make the most of this already, of this structure already. So from the shell, for us to be able to import and call our functions from other scripts, we're going to create this init files. And for those that are still very new to Python, this init files basically tells Python that we have a package and that we are going to have some functions that we're going to call from other scripts. So we're going to do touch from your shell, src data underscore underscore init underscore underscore dot py. We're going to repeat for src visualization init underscore underscore dot py. Be very careful with the underscore underscore, or it's not going to work. And repeat for our root directory of our source code, of course. Everybody here? So if you go to your Jupyter lab and you go to src, you should have an init. Then in data you have another one. And in this you have another one. Now we need to make sure that we can run everything from... our ultimate goal is to have just one script, one instruction from the command line, and everything will work. Again, we're going to reference everything. We're just going to call and execute everything from the root directory so that we don't have all of the problems with relative paths when we want to share our code with others. And there is a thing, you will remember from PEP that Python doesn't like it very much when you have your scripts or your modules starting with digits. It is recommended that you use letters instead of digits, sorry. But because we want to ensure that we know in which order things are happening and we are following our convention, we're going to use a dynamic import. Instead of doing our traditional from my package import my awesome module, we have to do a more robust import. So from our top directory, we're going to create a launcher. We're going to create... Oh, sorry. Ignore me. Yep. So from src, we're gonna add a text editor, and we're gonna add our modules like so. So we start with import lib. And after that, we're gonna tell subset is gonna be my import lib.import module dot data, because it's gonna be there, dot O1 subset data GP, and it is inside, oh, sorry, this should be SRC, ignore scripts, it should be SRC. And we're gonna repeat the same for the 3 modules. Yes, so it should be SRC instead of a script. Is that big enough? Oh, if I make it too big. Yeah. So I just give normally this name so that they pretty much match the same function that are performing. So I have subset, it's going to be that, plot ones, and then country sub. And by doing so, it doesn't matter if my modules start with a digit. Python is going to be able to discover my modules regardless. And we're going to save this and make sure to rename this as Ronald wine or wines.py. And then Jupyter Lab is going to be able to give you your syntax highlighting. Okay. So you should have now a Ronald minus wines.py, and you have already imported your modules. So I'm just going to add a comment here, import modules. The next step that we need to do is to ensure discoverability also at the big package or main package level. So in our SRC init file, we're going to add from dot, that is our root, import data, from dot import visualization. And we already have this file that we created before, so we can just add it like so. Okay, yeah. If you don't have touch from your Git bash, since we are using Jupyter Lab, you can just create. You can create everything from your launcher. Just click on the cross text editor and rename the file as minus minus init minus minus.py. Why? Oh, well, I just click on text editor. I normally do this from the command line. You can do either. Yeah, you can do either. It doesn't make any difference whatsoever. Excellent. So we're all here. And this is what you're gonna put your Python skills to the test. You can work in pairs, you can work solo, and try to run. Well, now that you have your skeleton, you have your modules imported, try and create your run all script. How would you go from step number 1, that is subsetting your data, to step number 3, that is subsetting again for your country? How would you integrate it in a single script that you only have to call from your command line Python run all wines.py, and it does everything for you? Okay, shall we give it 10 minutes, 15 minutes? You can work solo, you can work in pairs, you can you can ask for help. Is it clear? Yes? No? Are we running out of steam here? Is it lunchtime? Okay. Again, this should be easier. So once you have completed your run all script, probably you want to try it, and you'll have to run it like Python -m scr.runAllWine or run all wine analysis, however you call it. You're not gonna need the .py at the end. You're just gonna need the Python -m, and this tells Python that you're running from your topmost package, that you're running a script from that package. Okay, 10 minutes, 15 minutes to work in pairs or solo, whatever you prefer. Okay, how are you getting along? Not very good? Not running? What problem are we drugging? You don't have import lib. Okay. Yeah, so you have to do import.import lib. Import lib.import module. So in your run all. Yeah. Okay. So let's go over this. Remember, this run all should be inside your ISRC. You shouldn't have this. This is for my personal consumption now. So we're importing NumPy. Well, probably we don't need NumPy. Import pandas as PD. Import matplotlib, pyplot as PLT, and import lib. This import lib is the one that allows me to use my dynamic imports. So we change this. So that is SCR and SCR. A way to do this is to declare some variables there if you don't need to replace that. Otherwise, you can have that in a config file. I'm just going to set my raw data path to raw data. And it's going to be data raw, and that data set that is never going to change. I am interested in subsetting my country. It could be any country. It could be Egypt, USA, Mexico, Chile, Hong Kong, China, or whatever you want to add there. And then perform analysis, because we're running everything from the shell. We do the if minus name equals main. And this guarantees that if it's running from the command line, it's going to execute my analysis from there. I'm doing a subset file equals my library or my module is now renamed. I assign a variable, a subset. So I do subset dot process data GBP, and that's the actual function that is subsetting my raw data. What I am passing to that function is the path to raw data, because that is the argument the function takes. And I want to make sure that I get some feedback from in my command line or my terminal. So I do a print subset file, so I can actually see the path. Then I call from plot wines, that is my step 2. So I do plot wines dot create plots, and what I'm going to pass, the path from my subset data, because that's actually the data that I'm going to use for that second part of my analysis. Are we all okay here? Does that make sense? And then I'm going to create a second variable called country file. And it's going to be country sub, because that is my module that does the subset per country. Dot get country, that is my function. And I'm passing the subset file, that is the interim data. But I also have to pass the country, because this function takes 2 arguments: the path to the data and the country that I want to subset. Again, I hard-coded this inside here, so I don't have to feed any variables when I run this from the shell. And again, I want some feedback from my command line just to make sure that that is working. Okay, so if I wanted to run this, I have to do it again from the top level, from the root level of my project. So I do Python -m src run all wine analysis, because that's where it is. Ooh, and it doesn't like it. Oh. Where did I do this? Thank you. Okay. So did you try running this run all? No? What problem are we having again? We're dragging a problem that we saw before from the standalone scripts. The path, because we have a path that doesn't exist. So when it tries and plot again, it is going to say, I did the first bit. You can see that it's creating my interim data. Then I did something so that it creates a figure directory for me. If you didn't do that, it's going to complain and it's going to break there. So we've done a big leap now, and we have everything installed, everything automated. So now this is tea time, more than likely, more like testing time. We have everything, an automated script that should do everything, but we, cannot rely on the results because we've not tested anything. And we're still getting these problems with the paths because we've not put any measures in place to prevent this from happening. So we do need to do tests, and this ties it's more in line with scientific method. Normally what you do when you do experimental science is you do your experiments, then you test it and document it. So your code is not different. So you follow the same observation, hypothesize, experiment, repeat. And there are some approaches or different approaches that we can test. So we can do assertions to make sure that something is equal to something, like unicorn is equal to unicorn, let's say. Exceptions. Whenever we have exceptions, we're going to check warnings inside our script. So for example, these paths that don't exist, our Python code will check, does this exist? If it exists, it just carries on. If it doesn't exist, I need to do something to fix it. And then we can also do unit testing. As we have different functions and different modules, we want to make sure that each of that function is returning what they have to do. But this also helps us to identify bugs and identify those results that might not be very reliable. And finally, regression tests is we want to make sure that everything in our analysis is reliable and we can trust it, as well as integration tests. So if you go to your visualize wines, so if we go to our visualize wines, we can start and prevent this from happening. So where we have the F name, we're going to add this try. So in the first instance, you tell Python, try and save the figure in this F name that I'm telling you. If that fails, if you can't find a file or if you can't find the directory, then make this there called figures. And I wanted to say creating the figures directory just for me to have some feedback saying that it had to create it, that it was not existent before. And then it can save the figure. So this goes inside the plot distributions. And inside, and then you can copy that inside plot scatter. For this to work, is everyone here? For this to work, we also have to add this import. So we have to add import os at the very top, so that Python has the capability of creating this path. Okay. Once you've done that change, you've made that change, sorry, try to run it again. And you should see now a legend like this, creating figures directory. So now you actually see your script running. Okay? Have you got a fully functional automated run all scripts? Yes. This, yep. So we have done the very first layer. We started catching exceptions and programming with a defensive approach. This is likely to fail, but I don't want it to fail, so do this instead if you encounter this error. And that means that if your colleague runs this and he doesn't have the figures path created, this is going to be created for him or for you or for her, and then it will run as expected. Okay. So now we should have a fully functional run all script. Now we want to do some unit testing, and we're going to start testing our different functions. We're going to add we're going to open our country subset.py and add the following function. So just create a new function called def get mean price, file name. Again, this file name is going to take the CSV file, read the path to the CSV file. And then wine from pandas, read the CSV file, and then return the mean price of the wine. This is wine, price mean. And it's going to return the price rounded to the 4 significant digits. No. So you already have, yes, in your country subset, you already have all that you need, everything that you need. So you just need, the only thing you have to do is add this get mean price. Make sure to save it and make sure to actually be working on the script inside your reproducible Python. Okay. And we're going to create a testing suite, because we want to have our tests now independent from our code. So the same way we have a directory for our scripts, we're going to have a directory for our tests. So from your shell, again, from the top level, make their tests. And in your Jupyter Lab, you should see a tests file, a test directory. We're going to repeat the step of creating a init file inside my tests. Again, because I want this to be discovered as a test suite, as a test package. And since I modified the third script, that is the country subset, I'm going to create a test file specific for that. Make sure this is something mandatory, all your test files have to start with tests so that it can be discoverable as testing. Okay, are we all up here? Mhm. So inside, So inside that test 03 country subset.py, we're going to do the same thing we've already did. So do import lib, import our module, so you can copy and paste from your run all. Country import lib.import module data 03 country subset src. And then I'm going to create two variables here, one that is the interim data and the process data. So I give the paths. It's going to work for today because we have today's date and we also have that file use. So then you can use that as your base file or as your base data to compare against. Okay. Once we have done this, we can run it from our shell, just called PyTest. And because we have that structure that's we have our test directory and our tests files starting with test, PyTest will automatically discover them and run it. If PyTest encounters any errors or it is not working, it's going to tell you. It's going to tell you where it failed, why it failed. For example, in my case, I made the same mistake of importing scripts.data. It doesn't recognize that module, so I modified the path, the name of the module, and it works. There are two other examples of tests that you can add to this suite, but we're going to skip them. Other things that we can check is, for example, if we're getting a data frame, making sure that what we're getting in this case is actually a data frame and that it is similar to my raw data or to my that it hasn't been changed. We also sometimes want to run our results, but we want to add a tolerance. And NumPy allows us to do that. So instead of having an assertion where you say 2.5 equals 2.5, it says, well, whatever you're getting equals 2.5 within a certain tolerance, you could also do that. And that is very useful when you're doing data science things or data analysis. Now, I'm gonna skip this, and I'm gonna go directly onto provenance. Remember that I told you at the very beginning that provenance is tracking exactly what I did to get the results and know which version it is. So what I'm gonna do is, again, commit everything here, because now I have a testing suite, and we also have a fully automated analysis. And for me to track provenance, we can use a package called Recipe. And the only thing that you're going to change here is import the module Recipe here at the beginning. You don't have to do anything else. So in my run all wines blah, I just add that line. So I run it again like I did it at the beginning, is rc dot run all wines analysis. Oh, what did I do? Sorry, just need to make sure. Oh. Okay. So when you run it with the Recipe import at the top, you have Recipe run. You're going to see that it adds an extra legend, and it says Recipe run inserted with IV blah. So that gives your analysis a very specific hash. Now we can go Recipe as it is, and it gives you the option to, you have three options. You have this option, so you can use the Recipe GUI, the graphical user interface, just to make it a bit more intuitive. And it's going to spin another web application. And this is the beauty of it. It will tell you what outputs you got, what version of your script they were from, and also that identifier. It's going to also create a database for you. So everything, it's taking a while. So that everything has a unique identifier. And you can refer that to whatever you want. If you've been using a version control system, it will also show you the defs of your commands. I don't know what's taking so long. Oh, there you go. So to start with, it has already found 2 runs of my script because I ran it 2 times. And it tells you the ID, who run it, when, what is that I run, which is my absolute path, what is my environment, the inputs, and the outputs. And all you had to do was import that Recipe, and you have this provenance at all times. What is most, you can save everything as JSON, or you can annotate all of this. So if you wanted to annotate here, you can add a note and say, run for Python or for PyCon, or run for Noble. And all of that is going to be stored. So once you start running analysis, you can keep track of all your outputs and from which version they come out with. Isn't this cool? And all you had to do was just import the library and does everything for you. And the final thing, we're going to run over 5 minutes or so. But I want you to push everything to GitHub. We now have everything working, so we're going to push it to GitHub. If you're running the GUI, just click Ctrl-C. Ooh. So we're going to go to our GitHub account. and create a new repository. Okay. So I'm going to just call it repro Python because I think I have another one. And create repository. We're going to make it public. We don't need a README because we already have a README. We don't need a license because we already have a license from Cookie Cutter, so we don't need to add anything. And we already have our repository. Sorry, we have all of our git ignore. We have now a local copy of all the things we have done. So we can add the remote. It always gives you these 3 options to create a new repository from scratch, or whatever you already have on your computer to push it to GitHub, or import code from someone else's. So we're going to copy this from my shell and git remote at origin. Make sure to use a URL to your repository. Git push -u origin master. Okay. It should be pretty much instant, and you should have now everything in the repository. Okay. And I'm going to skip a couple of things, and I'm just going to go to the Synodo bit, because this is something very important. If we go to Synodo, okay, it's going to take me to my account. You can link this directly to GitHub, so it is easier for you to create your repositories, to share your content and create DOIs. So you go to Synodo, you link to your GitHub account, and you should be able to see your different repositories. If you go to your repository and then GitHub, and then what I created is called ReproPython. Ignore all of my repositories. Ooh, isn't it here? Yeah, if your repository doesn't appear, you just sync it. And once you have this, it will allow you to toggle it on. More than likely, it's going to ask you to create a new tag, and that is for people to be able to download that specific version of your project. And then you can generate this badge. Once you have the Synodo badge, you can add it to your repository. It's not finding it. For a strange reason, it doesn't like it. So I'm just going to go with this. So I have a repro project, toggle on, you should be able to see your new repository, and it will give you a DOI. Now this DOI is basically like having any, when you have this, people can cite your files, can cite your code at any point, it can give you credit for your code, and that is going to make massive impact on your analysis. Other things that you can do is not only having a DOI, but creating a citation file. There are two standards at the moment. One is the CFF, and then the other is code meta. I like using CFF, but I am biased because a friend of mine did it. So add a citation file as well as your DOI. Similar to metadata, make sure to add a message. If you use the software, please cite as below, so that allows people to cite it accurately and appropriately. The minimal information that you have to add is your family names, your given names. If you have an ORCID, add it there. If you don't have, doesn't matter. A title, a version. The version should match the tag that you have. The DOI is the DOI that you get here from Zenodo, and when it was released. The release date has to be matching the day that you created your tag. And there are also a lot of other additional resources that I put in there for you to learn more about metadata standards, to learn about the data science metadata schema, how to reuse data that is from Mozilla. Semantic versioning, if you're interested in how to actually assign appropriate versions to your code. And also to citation file format and code meta. They're pretty much equivalent. Just find whichever works better for you. As I said, I like CFF because I've been using it now, and I'm just comfortable with it. On the Etherpad, this Etherpad is going to be there for a very long time until Mozilla decides to die. So you can find it there at all times. And you should see a repository with all the workshop's materials. If you click there, that repository is completely public. It's going to be there. All of the slides are also in the form of Jupyter notebooks. You can see the DOI. You can launch this in Binder. There is a link to the slides, the link to the Etherpad that we've been using, so that's going to be there for perpetuity. You have the same materials that we've covered. We skipped some tests and some things on integration and continuous integration. But there is also additional materials on getting started with Docker. And I recommend using repo to Docker because that makes the creation of Docker containers very easy for beginners. So instead of you having to worry about Docker files and fiddling a lot with it, it uses the same engine that Binder uses. So it is very user-friendly as long as you have a content environment or a requirements.txt, it works out of the box for most of it. And also sharing your interactive notebooks using Binder. There is also a small guide on how, if you have, for example, analysis that depend a lot on Jupyter notebooks, and you want to share it with the world in an interactive format instead of a static version, you can do so using Binder. And you also have materials on how to do that. I'll probably be adding content on how to def and merge Jupyter notebooks, because that def and merging of Jupyter notebooks is very problematic. So I'm probably going to be extending the content. And that is it. Time flew. I had more material than the one we covered, so feel free to go through material, feel free to go through slides. You can drop me an email at any point. I'm going to be around in PyCon. You can ping me on Twitter if you want to have a philosophical discussion about reproducible research or food. I am up for it. Also, I have some better software, better research stickers there if you want to sell them. And that is it for me. Hope you learned something and you don't hate me now. And that's it.